Hey guys, so we're going to jump into chapter 7 here, which is all about chemical bonding. So this is where we get to figure out how things react, why they react, all that kind of fun stuff. So first off, I had to fix the slide, but now that we can see what we were talking about, the basic idea of how to predict what chemicals are going to react is to understand that atoms like to have 8 electrons around them. Okay, so we call that the octet rule. We're going to learn in 112 that it's more of like an octet suggestion, but for this semester, we're going to be using structures where almost everybody wants to have 8 electrons. The only one who doesn't want 8 is hydrogen and helium. Both hydrogen and helium only want 2. Okay, so everything else in the periodic table has to have 8 electrons when they form a bond. Okay, so one example of that is sodium and chlorine. Okay, so we learned that valence electrons are the outer electrons in the last chapter. And so in this chapter, we learn about drawing the valence electrons. So you start off with a symbol in the middle, and then you count the number of sort of groups in the periodic table to get to that element. So let me show you a periodic table. Okay, so when I say groups, what I really mean is the main group elements in this case, because chlorine is right here. Chlorine is right there. So it's in group 17. So I can figure out how many valence electrons it has, either by doing the electron configurations like we do in chapter 6. The shorthand one tells you how many electrons are in the valence shell. Or we can count. We can go 1, 2, skip the transition metals, 3, 4, 5, 6, 7. So everything in group 17 has 7 valence electrons. Group 16 has 6, 15 has 5, 18 has 8, so like that. Okay, so we start off with the symbol in the middle. I counted the groups and we realized that chlorine is in group 17. So it has 7 valence electrons. We draw them as little circles. This is hard to draw on the computer, but bear with me. We start with one circle on top, one on the bottom. Remember that electrons choose to stay as far apart as they can because they're all negatively charged. So they don't like to be close together. So I fill 1 electron on each side. That's only 4, and we said we need 7, so I'm going to keep filling in. Now we have 2 electrons on some of them, some sides. Now, electrons actually kind of like to pair up because they spin in opposite directions and it creates kind of a balance. It's like having 2 shoes, right? You don't want just a left shoe, you like to have both. This chlorine doesn't have an electron in this position. If it did, it would have 8 electrons and that'd be great, but it doesn't. So chlorine is going to react to fill this empty space in its Lewis dot structure. Sodium is in group 1. It's right here. That means it only has 1 valence electron, so we're only going to draw 1 dot. It doesn't matter which side we put it on. Just put it somewhere. This is an easy way to visualize what's going to happen. This electron is going to go into the chlorine's empty place. Now that might look like the sodium has no valence electrons, which it doesn't, but it does have core electrons, right? So if we write the electron configuration for sodium, it's 1s2, 2s2, 2p6, and the element chlorine has a 3s1, but when we take away an electron, it's going to come from that highest energy level. So over here, you could almost think of it like having no valence electrons, 3s1, 0, instead of 3s1. We lost that electron. So now it's just the noble gas core, which for sodium, the noble gas core is neon. So there's our noble gas core. We gave up 1 electron from the highest energy level, that's 3s1. We gave it to the chlorine, and that leaves us with a positive charge because we have 1 extra proton, right? So sodium, where are we at? Sodium has 11 protons normally and 11 electrons. So your charge is 0 for the element. But when we take away 1 electron, That means we get a charge of +1. So that's where this number comes from, +1. We don't always write the 1, but it's there. The chlorine took an electron. It has an extra one. So chlorine normally has 17 protons. It's gained an electron, so now it has 18 of them. So its charge is -1. So that's where this negative sign comes from. Okay. Now, one of the cool things about this is if we do the electron configuration for chlorine, it's going to be kind of like sodium, but we're going to add on to it. So as an element, it's going to go 2p6, 3s2, 3p5, because it's in the third period and it goes 5 into the p block. By getting another electron, its new configuration, it's the same stuff in the beginning, but now we have one extra electron and it has to go into the highest energy level available, or sorry, the lowest energy level available. So that would be the p6 here. This has the same electron configuration as argon. So chlorine gains an electron because it means it becomes electronically similar to argon, and argon is really stable. We call this iso, which means the same, electric. Whoops, I spelled electric wrong. Isoelectric, meaning same electron configuration as, in this case, argon. Sodium here is isoelectric with neon. If you can make an atom isoelectric with a noble gas, that is good. That is stable. Noble gases have 8 valence electrons. That's what makes them so stable. So if we can make these products isoelectric with a noble gas, then that's what's going to happen. That's the reaction that's going to occur. Okay, so with a similar idea in mind, we want to make a structure for magnesium chloride, and it says Mg with a subscript of 2 on the chlorine. That means I have 2 pieces of chlorine and I have a piece of magnesium. The chlorine is going to look very similar to this one. So we have 7 valence electrons that we're going to draw. Okay, I'm just going to go through this real quick. So there's our 7 electrons. The magnesium is in group 2, so that means it has 2 electrons. So clearly, chlorine still wants to have 1 each. So we're going to put 1 of those on each of the chlorine, and that's going to make 2 Cls with 8 electrons around them. And they each have a negative charge. They absorbed 1 electron. Plus, I still have an Mg, and in this case, this Mg gave up 2 electrons. We have normally 12 protons. It gave up 2 of the electrons, so now I've only got 2 there. So that means I got a positive 2 charge. So I write that as a superscript above the line to indicate that it's a charge. Okay, so for you guys, I'd like you to write a similar structure here. Do as if we were reacting K, potassium, and bromine. So do this real quick. Pause the video and do it. I noticed last time when I asked a lot of you to do tasks, you forgot to go back and do it. So make sure you pause it right now and do that. It is graded. Okay, so when we do Lewis structures, that is when we make a picture that's showing valence electrons, we start off by putting the element symbol in the center. Then we place valence electrons all the way around it, 1 at a time on each side, until we have up to 2 dots on each side. That's 8 electrons. That's really stable. When we have electrons shared between 2 atoms, that means they're bonding electrons, and they go in between the 2 symbols, so we can show what is actually connecting to each other. You can put 2 dots in between 2 atoms, and that represents a single bond. So that would look something kind of like carbon and hydrogen can do that. So that's a single bond. You could also draw it as a line. C H. So the line means 2 electrons as well. Double bonds look like this. You would have double means 2 times as much. So if 2 electrons make a single bond, 4 electrons are needed for a double bond. In a triple bond, you'd have 3, like this. Okay. Now, sometimes it's a little bit challenging to figure out if we're supposed to have a double bond or a single bond or what have you. So here's one strategy you can use. All right, we're gonna open up a whiteboard here for me to use. Or a blackboard, whatever, it's okay. Essentially, what we can do is let's make up a question. Let's do the Lewis structure for, let's do CO2 as our example here. So the question is, we have to do a Lewis dot structure for CO2. All right, so here's a way to approach it. We start off by adding up the total number of electrons that we have. So I count the valence electrons, total valence, I guess. So I count them from the periodic table. So carbon is in group 14, so that means 4 valence electrons. Oh, my whiteboard disappeared. I guess I can't change screens, hang on. So 4 valence electrons for carbon. Oxygen has 6, and I have 2 oxygens, so I have to account for the fact that I've got 2 oxygens in CO2. Okay, so first we're adding up all of our electrons, all of our valence electrons. So 6 times 2 is 12, plus 4 more gives us 16 electrons in our structure. The second step is to draw a skeleton, a proposal, and sort of an idea of where to start. Okay, so when you do your skeleton structure, the first atom in the list, in the formula here, is going to go in the middle. And then I'm just going to put the oxygens anywhere. You can put them up and down, you can put them sideways, it doesn't matter, as long as they're somewhere. And in our skeleton structure, we're going to assume everything is single bonds. So I'm going to draw a line in between the carbon and oxygen to make them connect. Then I'm going to fill in my octet. So the line means 2 electrons. So the oxygen currently has 2 electrons, and I just drew another. So that's 3, 4, 5, 6, 7, 8. So we do the same thing to all the atoms. We fill them all in. Right now, carbon has 2 in this bond and 2 in this bond. So I'm going to have to put 4 more. Now we're going to count all the electrons we drew in our skeleton. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 electrons there. Well, I did something wrong because I said we have a total of 16 available electrons, and I have way too many here. So now I'm going to try to use double bond. And it doesn't matter which one of these I pick, but I'm going to draw an all new structure. Oh, that shows up nicely. Okay, and so we're going to go oxygen with 1 double bond, and one of the oxygens has a single, and I'm going to fill in my octet again. Now I have 2, 4 here, 5, 6, 7, 8, 2, 4, 6, and then 8 here. And the carbon has 2 in this one and 4 in this one, so it only needs 2 more dots. So we're going to count it again. So we're kind of doing the same process again and again. We're going to count all the electrons and see if it matches our initial number. We have 2, 4, 6, 8, 10, 12, 14, 16, 18. So I got 18 electrons. Still too many. So I'm going to draw another structure. In this one, I'm going to put another double bond in, or I could even make this one a triple bond. It doesn't really matter, except that I like things to be fair to both oxygens, and it seems like putting a triple bond on one and a single one on the other isn't very nice. So I'm just going to choose to put a double bond on each side. Now, so that each oxygen has 2 sets of electrons on it that aren't bonded. That gives it 8 total for each one of those. And the carbon has 2, 4, 6, 8. So now I'm going to count it again. 2, 4, 6, 8, 10, 12, 14, 16. So now I have 16 electrons. So the structure that is correct is this one. Okay, so that's another approach you can use in addition to the method where you start off with the symbol in the middle and you draw one dot on each side. And each open space where there's not 2 dots, that's where things are going to bond. Okay, so just to practice our Lewis dot structures, hydrogen has 1 valence electron, so it's just going to get 1 dot. Helium has 2 valence electrons, so it's going to get 2 dots. Lithium's in group 1, so it just gets 1. Beryllium's in group 2, so it gets 2. Boron is in group 3, so it gets 3. So you see the pattern, right? On the periodic table, these are arranged in order. This is period 2, lithium, beryllium, boron, carbon. So with each, as we travel through the periodic table, we're adding 1 more electron with each group we go past. So oxygens have 6 because they're in group 16. Fluorines have 7. I think I do too many on my oxygen. Hang on. So 1 on top, 1 on bottom. My fluorine should have 7. It's a little hard on the computer. Neon has 8 because it's a noble gas. It's in group 18. Helium is the only noble gas that doesn't have 8. And the reason it doesn't is because it only has 2 protons. It's very small. So it couldn't hold very many electrons. Okay, so you can finish filling this in, but you're going to see a trend. Everything in the first column, group 1, has 1 electron. Everything in 2 has 2 electrons. 3 has 3. 14 is what it's labeled on our periodic table. But main group 4 has 4 valence electrons, and on and on. Okay. Okay, so the entire point of learning Lewis dot structures is not about the periodic table. It's really about how do things bond? What keeps two atoms together to make a molecule? And the answer to that is electrons. Electrons are responsible for atoms staying connected to each other in a compound. Sometimes when they come together, it forms an ionic bond. So we talked in last chapter that that's really about the difference in electronegativity. Okay, so we have to remember that the atom that loses an electron is called the cation because cations are positive. Okay, so the positively charged particle. All right, anions are the opposite. They're negative. They're negatively charged things. So when we were looking at the formation of sodium and chlorine, where the sodium gave up all of its electron to chlorine, this is an ionic compound because I have a positive thing, a cation, and a negative thing, an anion. Okay, anions tend to be nonmetals and cations tend to be metals. Okay, so when we draw Lewis structures for ionic compounds, we were drawing them in the beginning of this lecture as completely separate particles. That's because that's what they are. The sodium and chlorine kind of just hang around each other because they have opposite charges, but they're not as stuck together as other kinds of compounds. That means that the Lewis octet rule doesn't work very well. Unless you think about the core electrons, like what we were doing in the beginning of the lecture, where we look at sodium becoming isoelectric with neon when it gives up its electron. Okay, so we don't draw Lewis dot structures that are ionic with bonds in between them. We draw it like we did the sodium to begin with, where the Na is positive and it's completely separate from that chlorine that stole its electrons. Okay. So the ionic structures look different than the covalent structures. Covalent means shared electrons, and we draw bonds in between atoms to show that. Okay, so here's what it really looks like. You have some sodium and chlorine hanging out together. They're spheres because they're not actually sharing their electrons. Okay, so you can kind of think of it as a positive and negatives just want to hang together, so they do, but it's actually really easy to separate them. Okay, so if we look at magnesium, it has a valence electron configuration. So we can do the shorthand here. So magnesium is group 3. That means, or period 3, sorry. Neon is in group 18 right before it. That's our noble gas. So we would write neon as the core, and then 3s2 because it's in the second box of the S block on the third energy level. Now, the question to ask myself is it easier for magnesium to give up 2 electrons or to gain 6 in order to complete an octet? And the answer to that, of course, is it's easier to find somewhere for 2 electrons to go than it is to find 6 electrons to take. So that means that magnesium, and generally all metals, are going to give up their electrons because they don't have enough electrons for it to really be worth it. On the other hand, you look at aluminum. Aluminum is a metal, but it's in group 13. So it has a similar structure. It's neon, then 3s2, 3p1. So we have 3 valence electrons. We can ask ourselves the same question. Is it better for aluminum to give up 3 electrons or to take 5 electrons? The answer to that question is, of course, that aluminum will prefer to give up 3 electrons rather than having to find 5 electrons somewhere else. So aluminum is a metal because it's easy to give up its electrons. Let me erase this stuff for you. Okay, so aluminum starts off with a Lewis structure with 3 electrons on the atom. We give an electron to each of these fluorine atoms when it reacts, and it's going to form an aluminum that has 3+ because it has given away 3 electrons. And these 3 fluorines are a minus charge. Now we could draw the whole Lewis structure like this. We could name it aluminum fluoride, or we can draw the formula right here, AlF3. And so this 3 communicates that there's 3 separate fluorines involved here. Here they are. Oh, that's supposed to be an arrow. 3 separate fluorines go into that. Okay, so all that information is communicated in different ways, but it all means the same thing. Okay, so then we can kind of extrapolate from that. Fluorine and chlorine are related to each other, so they're probably going to react in a similar way. So if our product of reacting aluminum and fluorine together is AlF3, answer me this question. What is Al and Cl likely to do? Okay, so you can do the kind of the same thing. I'll do the lithium fluoride one for you and then leave the other 2 for you to do. So lithium is in group 1, its symbol is Li. Fluorine is in group 17, its symbol is F. Lithium, being in group 1, has 1 valence electron. Fluorine, being in group 17, has 7. So I have to ask myself, would it be easier for the lithium to find 7 of them or to give up 1? And the answer is, of course, that it's going to give up 1 electron, which means the fluorine has to take that electron. So now it has 8 electrons, and that's what fluorine wanted anyway. So you actually, if you're losing 1 and fluorine needs to gain 1 in order to be happy, then I only need 1 of each of these things, which is different from the aluminum and the fluorine that we just looked at a second ago. Each fluorine needs 1, but aluminum needed to get rid of 3. So you had to have 3 different fluorines to put that on. I want you to do the same thing with potassium phosphide. Okay, so potassium, you should know what element that is. Phosphide means phosphorus. IDE means an element. Okay, that is become an ion. So you're gonna use phosphide, figure out how many valence electrons it has, so you can figure out how many it needs, and you're gonna use potassium and do the same thing for that. And then you're gonna do sodium sulfide. Sulfide, of course, means IDE is an element, so that just means sulfur. Okay. So when we have covalent bonding, it means the electrons are being shared. Unlike ionic bonding, where one of the electrons, or maybe more, completely leaves the metal and goes somewhere else. In this case, the electrons are still associated with the atom, but now they're being shared by another atom. We can think about this as a probability, just like we were for individual electron orbitals in the last chapter. All right, so here is a picture of what a covalent bonding situation would look like. Okay, so we start off with two atoms, and when they bond, they share electrons. So it looks like just a smeared cloud in between them. That's really what molecules look like. The little dots in the middle, of course, are the nucleus. Okay, so you can see two little dots. The electrons are shared in a big cloud around it. Two of the electrons exist most of the time in between the two atoms, the two nuclei here. So since they're between the two nucleus portions of the atoms, we draw them that way when we're doing Lewis dot structures. So let's look at one that's a little more complicated. This is just two hydrogens. This next one is nitrogen, which has a core electron cloud. So here's our core cloud, this and this. These are core electrons. They're not directly involved in the bonding at all. The bonding is really from this kind of outer cloud here. Just the valence electrons are involved in bonding. So when we watch the animation, it starts off as two individual atoms, and then the outer layer kind of just smears together. That's what we're trying to communicate when we put the electrons in between the two symbols in the Lewis dot structure. Okay, you'll notice again that the core electrons on the inside don't change. Okay, they don't react. So the electron configuration of nitrogen, we start off, let's see, so nitrogen is in group 15 it looks like. So I have 5 electrons, but I have 2 nitrogen. So my structure needs 10 electrons total. I'm going to start off with a single bond, and then I assign 6 more electrons to each nitrogen because that's how I would get an octet. The next step is to count this. I got 2, 4, 6, 8, 10, 12, 14. I have 14 electrons. That's way too many. We said we needed 10. So I'm going to try to do a double bond. Now if I have a double bond, that's 2, 4, 6, 8. 6, 8. Okay. Now I got 2, 4, 6, 8, 10, 12 electrons. That's still too many. So let's try a triple bond. If we have a triple bond, that's 2, 4, 6 electrons already in there. We can just put 2 more on each nitrogen, and that'll give us the 8. In this case, we count it again, 2, 4, 6, 8, 10. So now this has 10 electrons, so this is the correct structure. Oops, I drew through it, but you get the right idea. Apparently, nitrogen has a triple bond. When we take a picture of what that looks like, it just looks like 6 electrons being shared in the middle of 2 nitrogen nuclei, like that. Okay. So when we share electrons in a single bond, it's called a sigma bond. The symbol for sigma is kind of odd. It looks like that. I'll show you one more time. You start here and you curl up, sigma. Anything that has a bond has a sigma bond in it. That's kind of like the default. That's the lowest energy level. So if I've got 2 atoms bonded together, I have a sigma bond. If I have a double bond, it means I also have 1 pi bond. Okay, so pi bond. A pi bond is kind of weird. It's made out of the p orbitals. It comes from p orbitals. So those are the ones that we were sketching that kind of go up and down like that, or side to side, or kind of front and back. In this particular case, we have the sigma bond in between, and the top and the bottom are caused by 2 p orbitals just kind of smooshing together. So a carbon p orbital and an oxygen p orbital get together and they just squish into this kind of cloud where electrons can exist. So that's the shape of a p orbital. It exists on the top and the bottom of the molecule. That's 1 orbital. So if you have a double bond, you have 1 p orbital. Well, sorry, 1 pi bond that is on the top and the bottom because it was a p orbital. If you have a triple bond, so if say you had that, it has 2 pi bonds. One that goes up and down, kind of like this, and another one that's in the front and the back of the molecule. So we have 2 pi bonds and 1 sigma bond. The sigma is the most protected, it's the strongest. Pi bonds are a little bit more vulnerable and weak, so they tend to be ones that react pretty quickly. The cool thing about it is the names kind of match. So S electrons are responsible for making sigma bonds. The S's again are the spherical electrons. Well, let's just erase all of it. If you need to write things down, go ahead and pause and do that. Okay, so S electrons form sigma bonds and the P electrons make pi bonds. So that makes some sense. Okay, so let's revisit the idea of electronegativity. We talked about it in class last week. We did some homework on it, hopefully. This figure from your text, oh no, from another text, is a little misleading, and you're going to find this all over the internet. What we use is the idea that the only thing that is really nonpolar is when the electronegativity difference between two atoms is 0. Anything bigger than 0 doesn't count as nonpolar. From bigger than 0 up to 2, we call polar covalent, and if it's bigger than 2, we call that ionic. Okay, so we noticed that the notes seem to have different versions of electronegativity tables. Again, the reason for that is that this is not an absolute scale. This isn't something you could actually just measure. You can't get a bunch of carbon together and find out how much they like to have electrons around them. There's no way to measure that. So instead we compare in multiple situations and try to get a feeling for how different elements react. And that's what these numbers are based on. When you take your exam, there's a link to a specific electronegativity table, and that's the one you should use for the test. Otherwise, you're going to get different answers because these numbers can vary a little bit. Okay, so we're looking at carbon and oxygen first. Carbon has an electronegativity of 2.4 and oxygen is 3.4. So in order to get the difference, I just subtract the big one minus the little one. So it has a difference of 1. That makes it a polar covalent bond because it's bigger than 0, less than 2. Hydrogen has an electronegativity value on this table of, where's hydrogen? There it is, it's over here in the corner, 2.1 right here. So if it's 2.1 and each one of them is a hydrogen, when I subtract that, there's no difference in electronegativity. So we call that non-polar covalent. And I'm going to bet the last one's probably ionic, but let's find out. Na and Cl. Na has an electronegativity of 0.9, Cl is 2.7. So according to this version of the electronegativity table, NaCl is not ionic because it's less than 2. That's different from what we saw in the one last week. I like the one from last week better. It has values that I think are more accurate, but you work with what you have. All right. So if I get a value of 1.8, I have to say it's polar covalent. This does not agree with our prior statement that a nonmetal and a metal together would make something ionic. Sometimes it doesn't. Okay. So I hope you know the trends by now, but just in case you don't, francium is the most metallic thing, helium is the least. So that means that your metallic arrows are going to go pointing towards francium. Okay, so we're going to do, show me the metallic and non-metallic trend here. Show me the atomic radius trend. You want to show me vertical and horizontal, not one or the other. You're going to show me the ionization energy and the electronegativity trends. Okay. Oh, look, there they are. Okay, so same slide we had in class last week. This is where we get to use it. Once we have a Lewis structure, okay, we can assign, sort of compare even, the value of oxygen and hydrogen. So oxygen is 3.5, hydrogen is 2.1. That means that this bond between them, this thing holding them together, is a polar covalent bond. The oxygen likes to hog electrons because it has a higher electronegativity than the hydrogen does. So the electrons spend most of their time kind of hanging out by the oxygen and less time over by the hydrogen. All right, so you have these answers from last week. Now I want you to draw Lewis structures here and predict whether their bonds are going to be ionic or covalent using electronegativity differences. This will be graded. So make sure you pause the video and you do that. Okay, so this next one is to practice using electronegativity. All right, and so our scale for our class is going to be anything 0 is nonpolar covalent, anything bigger than that and less than 2 is polar covalent, and anything bigger than 2 is ionic. So those are our cutoffs. You're going to see if you go on the internet and watch videos, each book, each person has a different cutoff, but that's what we're going to use. So don't be confused if you go looking for some help online. All right, so whenever I need to know whether electrons are shared equally or not, I'm going to use electronegativity. So in this case, if I do a Lewis structure where I have aluminum and chlorine, I could do one like this, where I have the chlorine singly bonded to the aluminum. That's a possible structure you might come up with. Okay, so that's what it would look like. Or you could think about it as an ionic thing, in which case the aluminum would be totally separate from each one of the chlorines, and the chlorines would have negative charges. Okay, I'm just going to write that there was 3 of those chlorines rather than draw each one, but you get the point. So in order for me to decide which one of these 2 is the best structure to turn in for my assignment, I have to know whether this bond is polar or nonpolar or ionic. So we're going to go back to our chart here in this. We're going to compare aluminum is 1.4, it says, and chlorine is 2.7. So those values are what we're going to use. Okay, so 2.7 minus 1.4 will give us the answer. Our trusty calculator says the answer is 1.3, which means it's polar covalent, somewhere in this area. Polar covalent. So that means this structure, the covalent structure, is actually correct, not the ionic one. So whenever I'm doing Lewis dot structures, it's always a good idea to make sure I've chosen the right way to draw it. We would have thought that aluminum and chlorine would form an ionic compound, but aluminum has such a high electronegativity for a metal that it doesn't. It actually is a polar covalent bond. Okay. So again, when we're thinking about multiple bonds, we need to understand that you can have a single bond, which is 2 electrons. You can have a double bond, which is 4. Or you can have a triple bond, which of course would be 6. 3 times 2 is 6. So bond means 2 electrons. Okay. Why do double bonds and triple bonds form? So that's a hard question to answer, but let's try it out. Hydrogen only has 1 electron each. So the only thing it can do is to share those 2 electrons between them in a single bond. It doesn't really have a choice because hydrogen can't handle anything more. It only has 1 proton. So trying to stuff more electrons around it would be really, really challenging. Oxygen, on the other hand, if we use our method of drawing a single bond between them and then filling in the octet. Oh, I forgot to add my electrons together, so I'm not even sure what I'm shooting for right now. Oxygen, let's see, oxygen's in group 16, so 6 electrons times 2, this should have 12. At the same time, I'm going to do nitrogen. Nitrogen's in group 15, so it should have 10 electrons because it says N2, so that's where I'm getting the 2. Okay, so if I draw oxygen with a single bond, it would need to have 2, 4, 6, 8, 10, 12, 14 electrons. It doesn't, it only has 12. So then this structure doesn't work. I'm going to try to make it a double bond then. Fill in my octet. So it's 2, 4, 6, 8. Now we have 2, 4, 6, 8, 10, 12 electrons, which is what we thought we would have. So this is the structure of nitrogen. I'm sorry, that was wrong. Oxygen. I want you to draw the structure of nitrogen here. And then tell me and fill in these questions also. We sort of talked about that just now. And tell me why do double and triple bonds form? What is it about oxygen and nitrogen that make double or triple bonds happen? Okay, so pause the video and do that real quick. Okay, so hopefully you've done that. I'll grade it when you turn your stuff in. The last little topic here in this section is really about the back of your periodic table, which we've kind of been ignoring all semester. I referenced it in lab probably last week, but one of the cool things is that sometimes compounds form really, really stable particles that have a charge. Okay, so all of those, the important ones anyway, are listed on the back of your periodic table. I don't want you to memorize the name or the charge, but we do have to learn to recognize when to look at the back of the periodic table. Okay. The reason it's important is because when I have one of these polyatomic, poly meaning many, so many atoms in a group, they stay together. They don't ever break up. We keep them together. They can connect to other ions though. So like one of my favorite polyatomic groups is called carbonate. It's listed on the periodic table on the back of yours. The one that I gave you, it's not on every periodic table, just the green one I gave you. So carbonate is this material, CO3 with a 2- charge. Carbonate can pair up with a positively charged thing because it has a negative charge. So if a sodium is anywhere nearby, the carbonate is going to be like, hey, let's hang out. We both have opposite charges. But one sodium is not enough because sodium has a positive charge and this has a 2-. So actually what we really need is to have 2 sodiums. All right, that balances the negative charge from carbonate. So the thing that would form between sodium and carbonate, which is the name of this stuff, it's pretty straightforward to name if you know what carbonate is, it would be Na2 because I have 2 sodiums on my picture, and CO3. The charges cancel each other out, so this is the formula I would write. All right. When this stuff reacts, it's not, the carbonate is going to stay together. The sodiums might go away, but the carbonate stays. Okay, so that's something really important we need to recognize. So we're going to practice using polyatomics quite a lot, especially in the next chapter. So it's a good idea to start recognizing those names and structures and charges. Finally, the last kind of bond we can have is a metal bond. These ones are kind of boring, to be totally honest. Necessary though, because without them we don't have electricity. Okay, so the reason we use copper wire to transmit electricity from national grid all the way to our houses is because they have metal bonds. And the basic idea in a metal is that the nuclei, the positively charged dense center of each atom, are arranged kind of in a geometric way, but the outer electrons kind of just flow wherever they want to go. So that's how metals behave. That's why metals conduct electricity and nonmetals don't. Okay. So we think of this as like a sea of electrons where the electrons slosh all over the place all the time. That's what a metal is. Every kind of metal you've ever seen behaves this way. Copper and iron and everything. Okay, but that's not much more we can say about that. We can't really draw Lewis structures of that because the electrons are not belonging to a particular atom. It's just something that we need to keep in mind that it exists. Usually, metals only lose 1 to 3 valence electrons to do this. Those ones are easy to take away. After that, it gets a little more complex. Okay, so that's the end of the notes for today. I have posted a homework sheet on Blackboard, an assignment for you to do. You need to work on that before class next time because we're going to grade it and we're going to talk about it, and then we're going to move on to Chapter 8. As usual, if you have any questions, please don't hesitate to email me or give me a call.